Hello everybody. So in this video, we're going to be talking about logarithmic functions. So we're going to just start off by defining what a logarithmic function is. So we're going to let a be a positive number with a not equal to 0. The logarithmic function with base a, denoted log base a, is defined by, and I'm going to zoom in here so we can actually get a really good look at this. And this is read log base a of x equals y. That double arrow means if and only if a to the y equals x. So log base a of x is the exponent to which the base a must be raised to give x. In other words, the letter a is going to be our base. That means the letter y here is going to be our exponent. And if we just transpose that information over on the right-hand side past the if and only if statement, notice here we have the letter a again, which is our base. And then the letter y, once again, is going to be our exponent. And then in the previous video, I also gave a picture of what these two things look like. And I used two very special situations. So let me go back over to here. Let me get out Desmos real fast. Okay. And the ones that I looked at were, first I said, well, y equals x. We're going to do a dotted line of that. And then I said, we're going to look at e to the x and then the ln of x. And if you notice here, and I'm going to try to zoom in as best I can, is that the blue line and the green line, which are e to the x and the natural log of x respectively, are mirror images of each other, which means they are inverses of each other. And remember, with inverses, you can always take a point like 0, 1 and just switch them. And that'll be the inverse 1, 0. And you can do that for every single one of these points from 0 to infinity. You can do that, okay? So now, what I want us to do is I just want us to kind of get used to like converting back and forth, all right? Evaluating logs, if you will, all right? So I got some examples here I want us to do. So let's go back into our notes. I'm going to write down evaluating logs. And here's some examples here. So first, we're going to do the log base 2 of 32 equals 5. And the reason for that is because 2 to the 5th equals 32. Now, let me show you how I got that. In red underneath, I'm just going to write out the definition of the logs. We have log base a of x equals y, which means if I were to kind of just like write these things down, a equals 2, y equals 5, x equals 32. So when I come over to the exponential form, when I come over here to the exponential form, I can go ahead and write a to the y equals x, or 2 to the 5th equals 32, okay? So I hope you see like just kind of how that works, all right? Let's do another one here. We'll do another one here. All right. So maybe I'll write the directions like this. Given the exponential form, (16 to the 1/2 equals 4. Write this in logarithmic form. Okay? So here's what we know. 16 to the 1/2 equals 4. So we know the 16 has to be the letter A. The 1/2 has to be the letter Y, which means the 4 is going to be the letter X. So in logarithmic form, which is log base a of x equals y, what we're going to write is log base 16 of 4 equals 1/2. And that's how we write it in logarithmic form. Okay? Now, we do have properties of logs, okay? And these allow us to simplify. So ways to simplify logs. And there are basically 8 properties. I'm going to give you the first 4 right now. So here's the first one. Log base A of 1 equals 0. Okay? Second would be log base A of A equals 1. And the key here is to recognize that if the base and the x are the same exact number, it will simplify down into a number 1. And I think a really easy way to kind of describe that would be to go ahead and write it in exponential form, okay? So for example, we know this is going to be the a, this is our x, which makes this y. We know exponential form is a to the y equals x. So therefore, if I just go ahead and make my substitutions, I get a to the first equals a. So you can see how these log properties actually are derived just by using the relationship of what a natural log is and its natural inverse, which would be an exponential form. Okay? So the third property here is going to be the log base A of a to the x equals x. Now, I'm going to put a star next to this one because that is one of my favorites, and we're going to be using that a lot when we go ahead and start solving different logarithmic equations. And then the fourth property right here is going to be a raised to the log base A of x equals x. Okay? So make sure that you understand these properties and make sure you know when you can apply them and everything. Remember, you can always go back to the basic definition of what a log is. And remember, I'm going to write it out over here to the right. Log base A of x equals y if and only if a to the y equals x. So in this situation, like let's say, for example, number 4, here's your a, there's your y, and obviously this is your x. So this is an exponential form, but if I write it in logarithmic form, I'm going to get log base A of x equals, oops, sorry, wrong variable. Now I'm getting myself confused there. I got to quickly look real fast. So we have log, so this is going to be the y. So it's log base A of x equals, and that'll be my a right there. Okay? So, like I said, make sure you know these properties here. We're just going to zoom up here. We're going to move up because we're going to look at graphs of logs. All right? And graphs of logs really aren't that difficult. All right? The thing that you really want to remember here is the domain and range. So, in general, y equals log base A of x is going to equal this graph right here. So we have a defining point, which is our x-intercept 1, 0. And let me change my marker here. This line, x equals 0, is going to be that asymptote that is similar to the e to the x one. So what I'm going to do here, just to make our lives a little bit easier, is I'm going to go ahead and just graph a couple logs just to show you how they work here. So we have the log base 2 of x, so that's in purple. Then we have the log base 3 of x, that's going to be in black. And then we'll do another one. We'll do log base, let's go 10 of x, and that'll be in red. And what you can see is my domain is going to be from 0, not including 0, and it's going to stay positive. So I think what I should do here is this. I'm just going to copy and paste this into our notes so I can write on it. All right, so here's the picture in our notes right here. Okay. And what I want to do is I'm going to write on this. So notice in purple, red, and black, they all have the same exact x-intercept, okay? Also, they all have this asymptote here at x equals 0, all right? Therefore, our domain for each one of these is going to be 0 to infinity. And the reason for that, remember, domain, we need to think x values, okay? So notice I cannot go any further than x equals 0 asymptote, all right? And I can keep going positive if I wanted to. So that's why our domain is 0 to infinity, not including 0, okay? Now the range, we need to think y values here. So our range, and I'll use a different marker here. Notice all these values are going down here, and they're always going up, all right? It doesn't, it definitely looks like it levels off. It doesn't level off, it doesn't get large very quickly, but it's still increasing. So our range is going to be negative infinity to positive infinity, okay? So, excuse me, so you're always gonna have that. The only thing is, okay, well, what if I start to do like translations here, okay? So like, for example, let's say I wanted to graph y equals log base 2 of x minus 1, okay? So the way that we approach this, all right, is we have our parent function, which is the logarithmic function. And in black, and I'm going to try to do this very lightly, it's going to look something like this. Okay? Like that's what the parent function looks like. According to log base 2 of x minus 1, what I'm going to have to do is shift my entire log down 1 unit. So I'm no longer crossing at 1 comma 0. Now I'm going to be crossing at this point right here where I put that little plus sign. This is going to be the point 1 comma negative 1. So I still have basically the same general shape. It's just now it's going to look like this. Okay? And as always, the easiest way to check yourself to make sure you're correct is go back over into Desmos. All right? You could do log base 2 of x, which is in, I guess, blue. And now we're going to do the same exact thing again, log base 2 of x minus 1. Oh, sorry. They don't want capital X. They want lower x, which is fine. Okay? Now notice, and I'm gonna type out these points because I don't want us to get a little confused. And I'll label them the same color. So we have 1 comma 0, and that's going to be in blue. That is for our parent function. Okay? And then in green will be the shifted y log base 2 of x minus 1. So that's going to be 1 comma negative 1. And I'll make that green. Okay? And I'll label it. So you can see how I shifted this down 1 whole unit. Okay? Now, another thing you may run into will be something like this. So example, we're going to graph y equals negative log of x. Okay? Now, there is one thing I do want to go over. If we just write log of x, it actually has a base. It's base 10. So if you were to look at your calculator and you hit that log button is base 10, no matter what. Okay? No matter which calculator you have, you hit the log button, it's base 10. Okay? So notice here, we have our parent function log base x, but it has a negative out front. So we're going to get the reciprocal of what we have. So we're going to flip this about the x-axis. So once again, lightly, I'm going to draw the parent function. So it looks like this. okay? And then in red, I need to flip this about the x-axis. So now it's going to come down this way. Cross here still, and then it goes like this. Okay? At the end of the day, I would definitely just use Desmos to graph these. All right? We live in a very interesting time where we have technology to help us do a lot of this stuff. But it's always good to know how to do it by hand. So in black, and I'll put it in dots. There we go. So here's our parent function right there. And then in red, negative log of x. And let me just change it to red real quick. There we go. Just so it matches our notes. And as you can see, we just flipped about the x-axis. So that's really what we're concerned with here, okay? Last thing I want us to look at is just a horizontal shift. Oops, let me change my marker real quick. So here's an example of a horizontal shift. So y equals log of x minus 3. Now notice the shift is inside of the parent function. So we know that's going to be a left or a right shift, okay? So as always, I'm going to start off with the parent function that looks like this, okay? Now, we're going to go ahead and we're going to do this horizontal shift. And if it's x minus 3, we know we're moving to the right 3 units. So this focal point is now going to be shifted 3 units to the right. So 1, 2, 3, which also means my new intercept, or I'm sorry, not my new intercept, my new asymptote is actually right here as well. Because remember, if the point shifts, everything shifts. So this is going to be x equals, let's see, 3, which is our asymptote. Okay? And our graph is going to look like this. All right? So, as always, you can always go back to Desmos just to verify that you're correct. So we have our parent function, which is log of x. Now we're going to type in log of x minus 3. And notice, let me zoom out here a little bit. Notice that I shifted this x-intercept 3 units to the right. So 1, 2, 3. So here's that shift. And my asymptote is now x equals, sorry, I typed the wrong number. Give me a second. X equals 3, and you can see that right here. So if I just turn off the parent function, I think now you can see how everything's working out here in terms of the horizontal shifts and everything like that, okay? So these are just kind of like the basics, okay? Now what I want us to do is I want us to kind of look at some, I guess, example problems using the common log, which is base 10, and then the natural log. I'm going to define what the natural log is for us. So the most common log that we have is log base 10 of x, all right? In fact, I'll put is y equals log base 10 of x. And this is if you were to just use your calculator anytime you hit the log button, it's going to assume log base 10. Now, if I wanted you to evaluate logs with different bases, there is a formula that we use to convert it to log base 10 so we can use our calculator. Otherwise, you would just have to kind of write it out and then circle your answer. But there is another common log. The other common log is the natural log. Now, the natural log is the ln of x. And I know we've all seen that before. However, to properly write it out, it's actually log base e of x. So this is the natural log. It's just so special that we abbreviate it with the ln. Sorry, somebody was at my door there, so I had to answer the door real quick. So I had to pause the video. All right. Now, we do have properties for the natural log. And they basically follow the same exact properties that we have before. So the first one will be the ln of 1 equals 0. The second will be the ln of e equals 1. The third property is the natural log of e to the x equals x. And then the fourth one is going to be e to the natural log of x equals x. And you can verify every single one of these by using the definition, which is the ln of x equals, actually, let me write it out. Y equals the log base e of x if and only if, e to the y equals x. So you can verify every single one of these properties by using our basic definition of logs. All right? So if we wanted to, we can evaluate logs. Again, it's just this time, we're going to evaluate the ln of e to the 8th. Now, using property 3, we get the ln of e to the 8th equals 8. All right? So this kind of piggybacks off of one of the most important ones. And last time, and I'll scroll up here so you can see what I'm talking about. So I put a star next to property 3, okay? And I'm going to put another star next to this property 3 because they're all the same exact property. It's just one deals with logs in general, and this is more specific. It's the natural log. What we say is, with property 3, we can actually take this variable and pull it out front. Let me show you. So here we have this exponent right here. I'm going to pull this out front to give me 8 times the natural log of e. Now, by property 2, the ln of e is equal to 1. So this just turns out to be 8 times 1, which is 8. And this is going to allow us to solve problems where the variable is an exponent. We've never looked at problems like that before, but we're going to, okay? So another example here for evaluating a natural log would be like the natural log of 1 over e to the 2nd. First thing I would do is apply my negative exponent rule to make this the ln of e to the negative 2. Then I would take that negative 2, pull it out front, and evaluate the natural log of e, which is by definition 1. So you would get negative 2 as a final result. Anytime we give you something like just find the natural log of 5, just use a calculator. Okay? Just use your calculator. You could easily go into Desmos or something like that. And I'm just going to type it in real quick so you can see the ln of 5. And Desmos down in the lower right hand corner of the window, it's like 1.609. So I'll just round to 2 decimal places. And we'll just abbreviate it as 1.61. Okay? So, like I said, just use your calculator. It'll be much easier that way. Other than graphing it and trying to estimate what it is. All right? And that's going to be it for this section. It's not a overly difficult section to get, but there is going to be a lot of rewriting and a lot of just practicing different forms, going back and forth. Okay? If you have any questions, just let me know. Other than that, I'll see you in the next video. Bye.